fifth video lesson in this lesson 3.1 is on the continuously compounding interest formula. They're going to do a little bit of a derivation on how that comes about, and it's important that you know where this comes about, so I am going to address this a little bit in this video. I will try to keep it as short as possible. Here's what we're looking at. In question number 4, in your textbook, this is where the example came from. It's the same type of problem that we did in the previous video lesson where we took an account balance, we put in a principal, and we started compounding more and more frequently. What we did here is they put in an amount of $300 and they started compounding it just annually, just once a year. Our value was $962.14. They started compounding more and more frequently. By the time they got done, they said, what if we compounded every hour? Well, every hour, you take 365 days of the year, you take it times 24 hours, you get 8,760 times of compounding on that interest, and now your money has grown to $996.03, which is a significant growth over what we had on an annual rate. But the growth that we see in between each of these, the growth is slowing down a little bit as we go to more and more compounding periods. So one of the things they're talking about, it does increase, but the amount of increase slows down as the number of compounding period increases. So it doesn't just keep ballooning faster and faster and faster. The growth rate is a little bit slower and slower as we do that. That's unfortunate. Super. I thought I just blew it up, but I think it's still going. So, all right. What we're going to do is look at a little bit of this derivation. The first thing they do is suppose your interest are compounded continuously so that there is no waiting period between interest payments. You're getting interest upon interest every moment of the day. So if that's the case and what is occurring here, then what we want to do is we want to see how they make this derivation of this formula. So we're going to start off with the compound interest formula that was given to us in the previous one. And then we're going to see how it becomes the continuous compound interest formula. So we start off with this idea that our amount that we're going to have after a certain amount of period with a given principal is equal to, and this is where our substitutions start to occur. So here's our first one. They say the compound interest formula with, we're putting in R over N, so that is this thing here written as 1 over N divided by R. Now this all works out, remember this is a double fraction bar, so this is really 1 divided by N over R, which means it's 1 times R over N, which is still R over N. So it's equivalent. This is a substitution that they're making here. So this N, or R over N, is being replaced with an equivalent expression of 1 over N divided by R. Okay, so then the next thing that they make here is another substitution, and the next substitution that they make is they're going to let x, and x is our value that we have down here. They're going to replace this n over r. So if x is equal to n over r, it just cleans up this form a little bit. So rather than having n over r, we got an x, which this implies that if this is true, then if I solve this for n, then n is equal to x times r. And you see that replacement is going to occur up in here too, x times r. Okay, so then we're going to proceed from there. Now they're going to use property of exponents. The property of exponents that they're using here is the power property. If you have something raised to a power, you multiply those exponents. So what I'm going to do is I'm going to break that exponent up, and the x is going to come inside here times RT. There's nothing that we've changed here. Everything is an equivalent form, just written in a different look or different variation. So they use the substitution of n over r. They replace that with x, and x is the same thing as n over r, but if we do that, then we can take out the n, replace that with x times r, and the x times r comes in here. Then we use the property of exponents, and that becomes x times rt as a power. This expression in the brackets, the thing that we're looking at in here, should look familiar because we saw it on page 160. They're saying that is the value of e. If we do the limit as x approaches infinity, if x is allowed to grow farther and farther, as bigger and bigger numbers, the actual value of that is going to become the value of e, which is about 2.1828. Get that right. And so on and so on. Okay, now here's where they start to think a little bit. They say if r is a fixed value. Now remember what r was. R was your interest rate. It's a yearly interest rate. So r is fixed. It can't change. It's going to be stuck down here and it can't move. As x approaches, so really I want to look at it like this. As n approaches infinity, and now what n stood for was the number of compounding periods, which we were looking at here. How many times a year are we going to compound? As we let that grow and it gets bigger and bigger, what happens to the value of this fraction? Well, if r has to stay fixed and doesn't change, and n gets to get bigger and bigger and bigger, then this fraction goes to infinity, which means they're saying x goes to infinity. So as n approaches infinity, so does x. So that means if we take the limit of n as n approaches infinity, so as the number of compounding periods approach infinity of this expression, it's really the same thing as this expression letting x approach infinity. And if we let x approach infinity, then the stuff inside of here approaches e. And e represents our natural base. So try to give a little explanation about what they're doing in there. If you still have other concerns or questions about that, just ask me in class. We'll go through it and I'll try to make more sense of it with you then. So what they're going to come up with is a nice little formula for continuously compounded interest, which means there's interest upon interest at every moment. So now we're going to take the same problem that we had earlier in the video 4. We have our formula says we can figure out how much money we have in our account. If we compound interest continuously, now our formula becomes P times E raised to the RT, where R stands for your interest rate as a yearly interest rate, and T stands for the amount of time you're just going to let it grow, and P is still your principal. Your principal is $1,000 is what we invested. We're going to raise E to the power of, it's still our 8% interest rate, so 8% interest rate times, we're going to let this go for 10 years. So really what we're going to calculate is 1,000 times E raised to the 0.8. And we can see how much money we'll have in our account after that. So last time we did that, we raised it, I got it on the board here. This amount here represented how much we had in it when we compounded it daily. So now we're going to do this as a continuously compounded interest. So we're going to take 1,000. We're going to take it times. Now E is a button you need to find your calculator. It's right under natural log, so I need the second. It's got an e to the x. It's got its own special key because it's such an important number. Times raised to the 0.8. Enter. How much money will we have in our account? You can see it's not going to be a lot different. All we're going to change it is by 20 cents approximately. So now in our account, if we compound continuously over compounding daily, it's $225.54. $225.54. Which again, you see some growth, but the growth is starting to slow down. This is using the continuously compounded interest formula. If you continuously compound your interest, this is the one you go to. Otherwise, you use your compound interest formula and based on the number of compounding periods.